Calculus, probability, and relations do not function on raw numbers alone. They require a rigid operating system to define what numbers are allowed to interact. That specific operating system is known as set theory. At its core, a set is a well-defined collection of distinct objects. In mathematics, we call those specific objects elements, or members. The syntax governing these collections is absolute. When placing elements inside curly brackets, any repetition is entirely ignored. Furthermore, the specific order in which you list the elements has no mathematical weight. Writing a set as 1, 2, 3 produces a mathematically identical object to a set written as 3, 2, 1. Translating loose linguistic logic into these absolute parameters guarantees that our logic holds up when we build more complex mathematical architecture on top of it. To put that architecture on paper, we rely on two standard forms of notation. This shows the roster form, a literal list of elements. Below is the set builder form, defining elements by a property, all x such that x squared equals 16. Solving this condition resolves it back to a concrete roster list, -4 and 4. Mastering the translation between a descriptive condition and a concrete list allows you to extract raw data from dense problem descriptions. Moving beyond pure algebra, complex logic problems require spatial representation. This diagram introduces the absolute domain of any given problem, called the universal set, denoted by U. Every calculation we make happens inside this parameter. Within that universe, we establish boundaries. If every single element of a set A also exists within a set B, we define A as a subset of B. The smaller set is completely enveloped by the larger one. A frequent trap on entrance exams is confusing the notation for an element with the notation for a subset. Look closely at the boundaries here. An element is a single distinct item residing inside a set's border. A subset is the entire enclosed circle itself, fully contained within the borders of another set. Establishing these spatial boundaries visually prevents critical structural errors when you calculate overlapping probabilities later on. To define the 4 core operations of set algebra, we map them as precise geographic coordinates. This diagram shows our universal box containing 2 equal partially overlapping sets, A and B. First is intersection. This specific region contains only the elements that exist in both A and B simultaneously. Next is union. This covers the entirety of the coordinate space occupied by elements belonging to at least one of the sets. Then we have difference. By calculating A minus B, we isolate strictly the portion of A that shares no real estate with B. Finally, the complement. This is the absolute inverse. The complement of A is everything in the universal space that falls outside the boundary of A. Treating set operations as specific geographical coordinates rather than abstract symbols allows you to navigate logic problems visually. This spatial mapping becomes crucial when we apply the algebra of sets. While many identities mirror standard arithmetic, De Morgan's laws introduce a unique logic that is heavily tested. This diagram presents the first of De Morgan's laws. The equation states that the complement of A union B equals the intersection of A complement and B complement. The left side calculates the union of the two circles, then highlights everything outside them. We can verify this by walking through the right side of the equation geographically. We find the region strictly outside A. Then we find the region strictly outside B. Finally, we isolate where those two external regions overlap. Both logical pathways map to the exact same shaded area. The geometry proves the algebra. Once the regions are defined, we measure their exact size using the cardinality formula. The total number of elements in A union B equals the number in A plus the number in B minus the intersection of A and B. The most common error in cardinality is assuming you can just add the totals of the two sets together. Notice how adding the full area of circle A to the full area of circle B causes their intersection to stack, double counting the center region. Subtracting that intersection exactly once corrects the overlap. The resulting union is flat, uniform, and mathematically accurate. Relying on this geographic visualization eliminates the rote memorization that often collapses under the pressure of a timed exam. The final application of set theory bridges directly into combinatorics. This transition happens through a structure called the power set. The power set is a master collection. It is the specific set that contains every single possible subset of an original given set. This leads to a guaranteed exam question. If a set contains an n number of elements, exactly how many subsets can you generate from it? This diagram maps the possibilities for a simple set containing the elements 1, 2, and 3. We calculate the total combinations using the fundamental counting principle. Every individual element faces an independent binary choice. It is either included in a newly formed subset, or it is excluded. Tracing that binary choice across the remaining elements creates a cascading tree. 2 choices for the first element, times 2 for the second, times 2 for the third, terminating in 8 distinct subset outcomes. Because every element always has exactly 2 choices, a set with n elements will always generate a power set containing exactly 2 to the power of n subsets. The power set illustrates how basic syntax inherently scales into exponential combinatorial power. When mapping these combinations, you have to account for the 2 subsets that always occupy the extreme edges of the calculation. First, a set is always inherently a subset of itself. Second, the empty set, a collection containing 0 elements, is a subset of every set. Failing to include the empty set when a question asks for the total number of non-empty or proper subsets is a guaranteed way to lose points on a test. We have moved from pure linguistic syntax, built spatial boundaries to map logical operations, verified algebraic laws geographically, and derived exponential combinatorial rules. Advanced calculus and probability do not tolerate ambiguity. Treating set theory as a rigid, infallible operating system provides the precise parameters required to parse and solve the most complex problems in mathematics. When we talk about relationships in mathematics, we aren't describing loose, intuitive connections. We are dealing with strict, calculable, geometric structures. To build one of these structures, we start with the absolute foundation, 2 non-empty sets, which we'll call set A and set B. This connection begins with the Cartesian product, the complete space of every possible ordered pair linking set A to set B. The geometry is predictable. Multiplying 2 elements in A by 3 in B yields exactly 6 pairs. Generally, m times n produces mn pairs. This brings us to the formal definition of a mathematical relation. A relation from A to B is simply any valid subset of this Cartesian product. Every specific relation from A to B is a precise selection of coordinates plucked from this complete grid of possibilities. Because a relation is a subset, every single ordered pair in the Cartesian grid presents a binary choice. It is either included in your relation or it is excluded. Each of the 6 coordinate pairs in our grid operates as an independent switch, flipping on and off. With 2 possible states per pair, the total unique relations generated is 2 to the power of mn. For our grid, 2 to the 6th yields 64. This number scales rapidly. If you are building a relation on a single set of n elements, the total number of possible relations explodes to 2 to the power of n squared. With a set of just 10 elements, you are looking at 2 to the power of 100 potential combinations. Most of these subsets are pure mathematical noise, completely devoid of useful structure. To make this space useful, we have to apply specific mathematical filters to sift through this abundance. Our objective is to isolate the ultimate structural tool, the equivalence relation. To build an equivalence relation, we must first narrow our focus. We drop the second set and look strictly at a relation on a single set, pairing a set A with itself. Let's define set A as the numbers 1, 2, and 3. Instead of a web of lines, we map this Cartesian product as a rigid 3x3 matrix, plotting all 9 coordinate pairs. This matrix allows us to visualize the first of our 3 filters, the reflexive property. Mathematically, a relation is reflexive if every element is related to itself. The pair A, A must exist in the relation for every element A in the set. When we apply this rule to our matrix, it locks in a specific geometric constraint. The main diagonal, coordinates 1, 1, 2, 2, and 3, 3, must be activated. The off-diagonal cells can be turned on or off in any configuration, but this central diagonal spine is non-negotiable. The rule is absolute. If even a single self-pairing is missing, the entire relation fails the reflexive test. Reflexivity establishes a structural spine. It guarantees a baseline of self-identity before any external connections between different elements are made. Once we have self-identity, we apply the second filter, the symmetric property. The definition of symmetry requires that if a relation contains the pair AB, it must guarantee the existence of its reverse pair, BA. This forces an immediate architectural constraint. Turning on cell 1-2 instantly triggers a requirement for its exact mirror across the main diagonal, cell 2-1. A perfectly symmetric relation will always identically mirror itself across its main diagonal spine. This is where many students preparing for the IIT JEE encounter a critical point of failure regarding a related term, the antisymmetric relation. Antisymmetric does not mean not symmetric. Treating them as opposites is a mathematical error. They are entirely different concepts. By definition, if a relation is antisymmetric, the existence of both AB and BA. Take the less than or equal to operator as the prime example. If A is less than or equal to B, and B is less than or equal to A, those two distinct nodes are forced to collapse into a single point, A equals B. Symmetry demands that a mirrored pair exists. Antisymmetry forbids mirrored pairs from existing between distinct, separate elements. We now have our matrix structured for self-identity and mirroring. The final filter required to complete our set is the transitive property. Transitivity operates as a mathematical chain rule. If the pair AB and the pair BC both exist in the relation, it absolutely forces the inclusion of a direct bridge, AC. Let's visualize this as a directed network. We have a path from node 1 to node 2, and a continuing path from 2 to 3. To remain transitive, these sequential links force a direct route straight from node 1 to node 3. The property only breaks if that first sequence exists, but the direct bridge completing the triangle is missing. A frequent exam edge case tests what happens if the initial chain from A to B and B to C never forms. In that scenario, the relation is still considered vacuously transitive because the condition to break the rule was never met. Reflexivity, symmetry, and transitivity represent three distinct geometric constraints placed on the Cartesian space to create order. So what happens when a relation survives all three of these architectural filters simultaneously? The relation graduates. It becomes an equivalence relation. See how powerful this is? We apply it to a classic scenario, congruence modulo 3, operating over the infinite, unstructured set of all integers. The rule for congruence modulo 3 states that two integers relate to each other if they leave the exact same remainder when divided by 3. We check our three filters. First, it is reflexive. An integer obviously yields the same remainder as itself. Second, it is symmetric. If integer a has the same remainder as integer b, then b shares that remainder with a. Third, it is transitive. If a shares a remainder with b, and b shares that same remainder with c, then a mathematically matches c. Because it passes all three tests, this relation now functions as an absolute mathematical sorting engine. When we turn this engine on, the infinite chaotic cloud of integers violently snaps into three highly structured, separated boxes. One for numbers leaving a remainder of 0, one for a remainder of 1, and one for a remainder of 2. We define these distinct, organized buckets as equivalence classes, and by creating these classes, the relation achieves our final theoretical concept, a partition of a set. A true mathematical partition enforces two strict conditions. It is exhaustive, meaning every single integer finds a home in one of the boxes, and it is disjoint, meaning those boxes absolutely never overlap. Every equivalence relation guarantees a perfect mathematical partition, transforming combinatorial chaos into absolute structural order. Clearing the IIT JEE requires a precise understanding of mathematical architecture. Success depends on viewing every equation as a set of rigid mapping rules. You learn early on that every function is a relation, but the reverse is false. Not every relation qualifies as a function. A relation is merely an association between two sets. It allows for a chaotic web of unrestricted, random connections. A function, however, imposes an absolute constraint. It is a strictly regulated mapping. First, every element in your starting set must have an outgoing mapping. Nothing gets left behind. Second, no starting element can split its output to multiple targets. If an input maps to more than one output, the structure breaks. Grasping this strict directional constraint is the prerequisite for classifying functions, chaining them together, and determining if they can be mathematically reversed. To analyze this architecture, we have to precisely label its parts. The valid inputs form the domain. The receiving set is the codomain, the universe of possible outputs. Realized outputs that receive an arrow form the range. Here, target C is missed, proving a strict rule. The range is always a subset of the codomain. Exam writers consistently test this distinction. Conflating the theoretical codomain targets with the actual hits in the range is a path to an incorrect answer. Once the sets are defined, we classify how the function claims its targets. A function is injective, or 1-1, if distinct inputs guarantee distinct outputs. If f of A equals f of B, then input A must mathematically equal input B. Plotting the linear function f of x equals 2x plus 1, we sweep a horizontal line down the graph to test injectivity. Intersecting only once means unique outputs. However, the parabola f of x equals x squared fails. At y equals 4, it hits two intersections. If a horizontal line cuts a graph more than once, multiple inputs share a single output. This qualifies the function as many-one rather than one-one. Next, we determine whether the target set is entirely filled. In an into function, at least one element in the codomain is left orphaned without a preimage. A surjective, or onto function, is defined by resolving that exact problem. Every element in the codomain now has an incoming arrow. The strict algebraic proof for surjectivity requires that the range perfectly equals the codomain. Verifying surjectivity means proving there is zero wasted space in the target set. Every potential output must be a realized output. But what strict mathematical conditions allow us to take this entire system and perfectly run it in reverse? A bijection passes both tests simultaneously. It is completely 1-1 and onto. Algebraically, for f of x equals 3x plus 2, we set it to y. Swapping the x and y variables and solving for the new y yields the exact inverse function. Only bijections are invertible. If a function is not 1-1, reversing the mapping splits inputs. If it is not onto, reversing it leads to dead ends. Once you have defined your functions, you can chain multiple mapping pipelines together in sequence. For g of f of x, apply f first, feeding the output into g. Squaring 2x plus 1 results in 4x squared plus 4x plus 1. Reversing this order to compute f of g of x yields 2x squared plus 1. Notice the glaring mathematical discrepancy. Function composition is non-commutative. The order of operations dictates the final mathematical architecture. Answering high-yield function questions requires a strict diagnostic checklist. You must ignore pure intuition and strictly follow the framework. Step 1. Explicitly identify the domain, codomain, and range. Step 2 and 3. Test for injectivity using the horizontal line test, and check surjectivity by verifying range equals codomain. Step 4. If both pass, declare the function bijective and clear for invertibility. When composing functions, evaluate the inner function first to avoid common errors associated with non-commutativity. This diagnostic framework provides a consistent method for evaluating functions. Even when the algebra is complex, the underlying mapping rules remain visible.